Hey, this is Don from Padlock Technologies again with another video. I know you guys are probably wondering, I haven't uploaded in a while, what I've been up to. So, really simple, learning AI networking. Um, this video is actually going to give you a wide overview or a big overview of what AI networking is. It's a pretty cool thing. It's definitely different from your standard traditional networking for data centers and stuff like that because there are different components. Now, I'm going to give you a high level overview of AI networking. I'm going to show you diagram of what it looks like, and I'll explain the pieces as we go. Again, this is high level. This is not going to get down into the packet types because this will be a 3-hour video if we get into that. If you are interested in more AI networking content, put a comment down below under this video, and I'll start to slowly roll out more and more stuff about AI networking. AI is here. You're not going to be able to get away from it. But as a network engineer, you really only need to focus on the networking part. The problem that I see in the space when it comes to AI networking is they really focus on the software engineering side of it. They really focus on, oh, flops and hallucinations are AI flywheel, which is basically a loop back system for AI to learn. But as a network engineer, you're really focused on building the railroad tracks, not the train per se, right? The train is the server, the data, all that good stuff. You're trying to make the best railroad track to get that train, which is data and stuff like that, to its destination as fast as possible. So I'm going to just strictly focus on the networking part because this is a networking channel. This is not focusing on AI agents and NIMs and stuff like that, how to build AI agents. This is strictly the networking part. So let's go ahead and go in the lab here and I'll pull up the diagram and I'll explain every piece. All right. So here is the lab. Now what I'm going to do first is I'm going to zoom out real quick so you can see in a nutshell how big this is. So this is the AI network. Now, doesn't technically, this could be a couple racks really, but this is to demonstrate the different fabrics that you're going to need to do AI networking. But this can be, a couple racks or a whole data center, depending on how much you want to do. So now let's focus on, there's three networks. There is the GPU backend, there is the front end, and there's the storage network, right? Which is the storage backend. So what we got here is we're going to focus on GPU backend. Now the GPU backend, this is where you have those NVIDIA servers or NVIDIA servers, however you want to pronounce that company. You know what I'm talking about. So you would have the GPUs, right? Servers right here. And I just use some generic icon, but these are like H200s. Now, NVIDIA does have I think it's the DGX series, but in each one of these servers can house, 4 GPUs, 8 GPUs, 16 GPUs, 30, 32 GPUs, whatever, right? Now, the GPU backend can be one or two things. It's either going to be a converged Ethernet, which is Rocky V2. Now, Rocky stands for RDMA over converged Ethernet. Now, RDMA is the protocol for the GPU backend, and this is supposed to be, lossless. It's the RDMA information basically is the whole frame. It's not chopped up or anything like that. If it's Rocky V2, that's a little different. But you got InfiniBand, which NVIDIA owns, and they have their completely own infrastructure, right? It's like you can make switches and stuff for InfiniBand, but you got to license InfiniBand from NVIDIA. Now, InfiniBand is pretty expensive, but it's highly reliable and super fast, right? So basically, what RDMA is, it's called Remote Direct Memory Access. So what it does is it will send information from GPU to GPU, bypassing the CPU, and go directly into the buffer or the NIC, go through the network, and go directly into the buffer on the other GPU. So that lowers the latency because you don't have to worry about it going through the operating system or the kernel to do the processing there and then sending that information out. So this goes completely around the operating system in the kernel, right to the buffer, gets sent through the wire, goes to the other buffer, right to the application. It does not go through the OS for that. So that's why the latency is super low, right? You probably see that in HPCs, where high computing, high performance computing networks, right? So they use the same technology. Now, Rocky is basically taking that same technology, it's wrapping it in an Ethernet frame, which is wrapped in an IP packet, right? So you can route it and stuff like that. Now you're going to have your typical spine leaf architecture. Why? Because you're trying to eliminate spanning tree in a data center. If you're doing stuff like this, you do not want spanning tree blocking any ports or doing anything stupid like that, because that's a lot. You can crash the whole AI system if some of this stuff gets out of sync. So you do not want spanning tree causing a problem. So you can have your typical spine leaf architecture, depending on what you're going to use, right? If you're going to use Rocky V2, you'll probably do something like Nexus dashboard, create the fabric here, and then you'll just run your fabric through Nexus dashboard for all three fabrics. If you're going to use InfiniBand, you would basically use things like Cumulus Linux, which is open Ethernet, which is a pretty cool thing too, right? Like it enables you to get switches, like bare metal switches, and then install whatever operating system you want on it. But again, that's a totally different topic. But this design here is called rail optimized. So rail optimized, basically each GPU, and I have four links here, right? So each GPU in each box is connected to its rail or leaf switch, right? And when you could do that, you basically stop traffic from ever having you reduce the traffic having to go through the spines, right? And that's what you really want to do, right? Because you can do rail optimize, or you can do this thing called typical spine leaf, where you would have all four links from the GPU server going into its respective leaf switch. But what does that do? It forces traffic to now have to go through spine switches to get to the GPUs, right? On another leaf, which is not you can do it, but it's not ideal from a bandwidth utilization standpoint and from a latency standpoint. When you do rail optimize and everybody's plugged into the same leaf at the GPU level, you never have to go up to the spine to get to another GPU in its other server. Because here's the thing, if you're doing some type of computation with AI and it goes past the GPUs that's in the box, it has to now use another GPU. Well, you don't want to have to go through the spine to get to that GPU, even though you can do it. It's just you're going to increase the latency, and you're trying to minimize latency. So if everything is local to each server, no matter where they are, because they're plugged into the same rail, it optimizes it, makes it more high performance when it comes to AI GPU backend, right? Again, two, spine leaf, rail optimized. If you look at the documentation, you watch any other videos, or you just go into a deep dive, they will always recommend rail optimized design. Okay. And you can technically go, if I can move this up a little bit, this could be 100 gig, 200 gig, 400 gig, 800 gig networks. And this is going to use a lot of compute, right? A lot of compute power is going to be on this GPU backend. You don't want to actually put your storage network and your front end in something like this. You kind of want to have a GUI backend already built or not GUI, a GPU backend just for the computation part of your AI infrastructure. Now, you have, depending on what you're doing, so if you're training the model, you're going to have a bigger network. If you're tuning the model, the network's going to be a little bit smaller. And then if it's a production network, it could be even smaller, right? Depending on what you're doing with the model. So that's the GPU backend. That's strictly for inter GPU communication. Intra GPU communication is going to happen within the box on the bus, right? That's in the box itself. When it has to go and use another GPU, that's the inter GPU communication. So you want to use this rail optimized design so that it doesn't have to go through the spine to reach it, right? So you're reducing the latency. Now this is all going to be, again, RDMA for InfiniBand, or Rocky V2, which is RDMA over converged Ethernet. And RDMA, once again, is just a protocol that's used bypassing the operating system, sending the information straight to the application buffer, right, without being processed by the OS or the kernel. So that's strictly for the GPUs. So how do you manage these things? Well, you have the front end, which will be over here. So your front end is how you're going to actually interact with AI, right? So what you're going to do here, and they call it inference, and you will just interact. This is basically interacting with the prompt. So every one of these servers are going to be hooked in to a front end because they're going to be there's ports on the back, or I think it's on the back or on the front of the box, but there are ports on the box just for managing and interacting with the GPUs and the AI, right? And that's your front end. Another thing, the front end and the storage network can technically be in combined fabric if you want to do that. But if you look at most design architecture white papers, they have the three networks separate. They have a separate storage network, separate front end, and a separate GPU backend. You're always going to have a separate GPU backend. What you want to do with the front end is really up to you, and the storage is really up to you at that point if you want to make them on the same fabric. All right, then you have your out of bound management. This is stuff where you're going to be interacting with the fabric itself. So you would have like Nexus dashboard or something like that to interact with the fabric out of band. You have your management servers and stuff like that. Obviously, that's going to be talking to the GPU network and then the storage network back here, because you can see these connections are here. And then you'll have someone, I didn't put the person out here, but you'll have someone doing inference, basically messing with the prompt or interacting through prompts, talking to the server, which obviously talks to the GPUs. And then all the training data is stored in the storage network, right? So you see the management network, management front end actually is tied into the storage network, and the GPU network or the GPU servers are also tagged, are they're actually connected to the storage cluster or the storage fabric, because all the training data is not in the GPU backend, right? That is just for the compute part, right? And to get data and do the computation and all that stuff. But all the training data is going to be in the storage network, right? That's what is going to do the crunching, getting all the data, learning, doing the AI flywheel, stuff like that to interact with you on the front end, right? So you guys behind the scenes are you on the front end, you see a prompt, but behind all that prompt is all of this, literally all of this. So you have your, you know, this fabric, which is your GPU backend fabric. That's to crunch the data. Then you got your storage network to hold the training data, right? Now, again, this is to train your AI model. I just built this out for training. When it comes to fine tuning, you're still going to have storage because you're going to have to fine tune your model. And then when it's a production model, your storage network may not be as big, just like your GPU backend may not be as big, and your front end will probably be small as well, because now when you're in production, you're not really fine tuning it anymore. When you're training it, obviously you need as much power as possible to train it as fast as possible. And that is the AI networking in a nutshell. Super, super high level video here. I could have went into a little bit more from a design standpoint, but I want to ease you into AI networking because most of the videos I see, again, they talk to you from a software engineering standpoint. They don't really talk to you about from the AI standpoint, especially when you get into cool stuff like open Ethernet, and you start talking about Cumulus Linux or Sonic or something like that, and you start realizing like, yeah, this completely is different from what you already know from the GPU backend standpoint. If you've been doing anything with VXLAN, MPPGP, EVPN, ACI, Nexus dashboard, you kind of know what a spine leaf cloth fabric is. You know what that is already. You just need to know, how do I build it for AI, right? And for the most part, you're not really going to use ACI for the fabric build, because I think Nexus Dashboard has a template already to build a Rocky V2 fabric, with because you have certain things like ECN and PFC, which are just congestion management stuff that is in a template that automatically creates a QoS policy to handle like congestion and stuff like that. So that's why you kind of lean towards Nexus Dashboard when you're building AI networks. So hopefully that was it. And I hopefully you guys followed exactly what I was saying. If not, rewatch this video. This is AI networking in a nutshell. If you are a network engineer, you cannot avoid AI networking. Is almost like how we used to try to avoid programming, and then network automation came in, and then we're kind of forced to be somewhat of a programmer. Same thing with AI. They're going to be building out these AI data centers. You at least need to be able to talk some of the lingo and understand, hey, what the GPU backend is, hey, what RDMA is, hey, what rail versus spine leaf architecture is. Why is rail better than spine leaf architecture? What is the front end? What is the storage back end? And stuff like that. That's really all you need to know from the networking side. Now, if you want to get deep down into like learning how AI functions, now you're going to start moving into the software side as well, because you're going to need to know a little bit about, well, not a little bit, but you're going to need to know how AI works at a fundamental level. Network engineers, we just need to know how to build the track. So this is Don from Padlock Technologies again. Hopefully you enjoyed this video. I know this is probably new to some people that's on the channel. Watch it again if you don't understand it, and then start researching on your own other videos. Don't just watch mine about AI networking and how to build fabrics for AI. Tom Padlock Technologies again. Thank you and have a nice day.